Welcome, my name is Simon Birrer, and in this talk, I'm going to talk about recent progress we made on shedding light on dark matter and dark energy with strong gravitational lensing. It's going to be two topics being discussed, the first on dark matter and then on dark energy, in particular measuring the Hubble constant. Starting with the first one, here is an illustration about, on one side, how strong gravitational lensing bends light and distorts the appearance of background sources. And we can measure these distortions on small scales to effectively try to distinguish different scenarios of the model of what dark matter is. So on the top is cold dark matter, while on the bottom it's a sterile neutrino, warm dark matter model. And we aim here to combine different cosmological probes, in particular strong gravitational lensing on one side, and on the other side, dwarf galaxies in our Milky Ways, to get a coherent picture emerging of not just what is the luminous parts that we see, where we see the stellar light of it, but also I want to detect effectively the dark, there are no stars in there, the dark clumps in the universe. And we would like to know the relation, are there this dark substructure, or can we live in a universe where we don't see the bright parts, but where there is no additional dark structure underneath. And so the first and it's most focusing is on gravitational lensing, and in particular here the probe of Flux-ratios. So how does this work? This is a movie illustrated that's made by Daniel Gilman, showing that a perturbation in structure in the lensing affects the magnification and distortion of a background's compact source. And we have worked over the past years in effectively end-to-end forward model these effects on the scales that we have the data. So we render different scenarios of what dark matter is, what other components of the universe are, and then do a simulation-based inference with approximate Bayesian computing on the data sets that we have to see which aspects are constrained by the model and which dark matter scenarios are favored in a likelihood sense. So this we can do on imaging data, as we've done in the past, and then pushed over the last few years by, in particular, Daniel Gilman in forward modeling Flux-ratio statistics. So how the ratios of different magnifications in quadruply lensed quasar imprint the statistics of the underlying dark matter structure. So we have our current constraints about 5.2 keV can be ruled out with 8 quasars alone. And in the next step, since I was in Stanford, we joined up with the team that did a similar analysis in spirit on the Milky Way's dwarf galaxies that derived constraints. And what I really want to emphasize is that the complementarity of these different small scale structure probes that we have really provides different views on the problem of dark matter and on the solution, I have to say. And so these distinct aspects, when combined self-consistently in a joint probe, really give rise to additional constraints. And that's what we've done here. This is work led by Ethan Nadler at Stanford, with myself and Daniel Gilman and others to have contributed to both sides of the probe. And this joint analysis pushed the limits to 9.7 keV at 95% confidence. So just to highlight here the opportunity we have when combining different probes. What we haven't combined in this picture is Lyman alpha forest, for example, or other small scale structure probe as stellar streams. And we push towards a combined probe analysis. So that's on the dark matter side. And now I want to come to the dark energy side, or in particular measuring the Hubble constant with time delay cosmography. Here, this is the one slight introduction of what we actually do. We're making use of the relative time delays from a variable source, in particular a lens quasar in that case. And by at the same time measuring the relative distortion caused by the foreground deflector, we effectively get a measurement of the path length involved in the problem. And so this is the absolute scale in the problem. And so we can measure then the Hubble constant as the inverse absolute scale. So what I have presented last year here, this is the update from TDCOSMO 4, where we relaxed significantly the assumptions that we previously used and added additional data, where we then came to results when adding with slacks to be consistent with Planck and about 1 sigma off from measurements from the Shoes team. And I will not go into detail of how it came to this measurement and what it includes, because I have presented them in last year's Cosmology from Home. So if you're interested in a 20 minutes presentation about it, you can go on click on this talk, and a 40 minutes Cosmology talk goes a bit in more detail into this. So here, shout out to the Cosmology talk format.
A postdoc at Stanford. He's here today to talk about.
And so to highlight here what the people have also asked me in the collaboration, so how we can interpret these results and what we have since then done. So the top here are the constraints on the mass profile derived from TDCOSMO 4. What we have since done, and this is work led by Anwar Shachib, using the same data on the SLAX lenses in TDCOSMO 4, has an interpretation of these mass profiles in both kinematics and lensing observables in terms of contraction and expansion of the NFW halo of the dark matter components on one side, or a slight gradient in the mass to light ratio. So these are physical motivated parameterization in the flexibility of the mass density profiles of massive elliptical galaxies. While in TDCOSMO 4, this was basically a front-on empirical parameterization to tackle the mass sheet degeneracy as a measurement of time delay cosmography. While here we have an interpretation of these measurements in terms of physical properties of these galaxies. So I recommend checking out this paper by Anwar Shachib. And we have also here, this is a summary of the TDCOSMO projects and the different values that are being presented in the literatures with the decision tree, so to speak, on what assumptions you want to rely on. What I also highlight is that in the assumptions of the power law stars plus an NFW profile, it also requires a constant mass to light ratio, as well as certain priors on the mass concentration relation and the masses of the halos, while these priors are not necessary for when we relax the assumptions and only derive the constraints from the kinematics. So that's for now, but I now would like to use this additional time in this video to look in the near future. So what do we have in hand, and what are we working right now on to shrink the error budget? And there are various surveys and capabilities available or getting available very soon to do so. And one thing we looked quickly after TDCOSMO 4 came out is looking in investigation within the same framework. What does future, in particular James Webb Space Telescope, spatially resolved kinematics, or the ELTs, provide us in constraints? And it really showed that the spatial resolved kinematics can bring us back to the errors that we had previously, or even shrink them to almost 1% budget with a sample that we expect to have in hand in the near future. So this is one approach to go forward. What's been circled around in the literature and actually finally also been discovered in the last few years are lensed supernovae. And these provide additional samples as well as advantages that we have. So advantages are, for example, characteristic light curve. So we are able to to characterize the time delays on shorter time scales and more precisely. Then when the supernova faded away, we can also do the stellar kinematics measurements without the hassle of having bright contaminations of quasar light in the vicinity of the deflector galaxy. So this can provide additional advantages for the stellar kinematics measurements. And thirdly, the standardizable nature of supernovas can help us effectively pin down the lens model and to break the mass sheet degeneracy precisely at the locations where we actually require them. And so with a team, I looked into this particular third part to effectively apply the TDCOSMO 4 formalism on standardizable magnification and see how well can we actually break the mass sheet degeneracy independent of kinematics with such an approach. And this is work in progress with Suhal, Dhawan, and Anwar Shachib. And here we have a forecast for different micro-lensing scenarios that to first order results in a scatter and an inflated uncertainty in the mass sheet term that we expect to really pin down the mass sheet transform independent of kinematics to sub 2% within a LSST survey. So this is really prominent and independent anchor and completely complementary systematics in the key uncertainty that we currently have. Looking further ahead, when we are dealing with a lot of samples of lenses, we need to take into account the covariances in the analysis, in the parameter inferences, in the assumptions we put in. And this comes with a price, both in terms of like how much analysis in terms of speed and in terms of accuracy on the population level. And the team at Stanford, this is led by 2 PhD students, Sebastian Wagner-Carrena and Siobhan Park. We put in a lot of work in actually making use of Bayesian neural network and hierarchical inferences to effectively debias the priors that we put into the training set in the inference and ensure that we get statistically accurate parameter estimates. And so I highly recommend checking out these papers and the GitHub repos that present the full workflow from the training set, the analysis, and the post-processing, so the hierarchical inference of this work. And this is both in terms of speed and accuracy required in the near future with the upcoming surveys. So that's one approach. Another work I want to highlight that I've looked into detail in the last year is what does strong lensing measure? So we need to decouple the actual observables from the model assumptions. This becomes more and more relevant the more lenses we deal with and the more we actually shrink the error bars. And so we can we found a weak and strong lensing unified description of curved arc formalism that allows us to gain further insight in what are actually observables and what are degeneracy inherent or that are being broken by certain model assumptions. So radial azimuthal constraints on the observables are illustrated here, and radial constraints can be decoupled, and we can then better know what are actually model assumptions and what are observable constraints directly. So check out this paper. And last but not least, also advertise the public available software here, Lenstronomy. There are also other public available softwares available that are in that sense affiliated with Lenstronomy, that are built within the ecosystem of Lenstronomy. Can be wrapper or full-fledged analysis pipelines on top of it, or making use of Lenstronomy. And we recently put out an updated Lenstronomy paper on JOS that also highlights the progress that's been made by the community, the development by the community, and links to all the affiliated software. So check out the software. And with that, I stop here. And thank you very much. And I'm looking forward for the discussions. And email me, get in touch with me if you have questions, if you're watching that on the web on a later format. Thank you very much.